My name is Ahmad Abdulkader. I'm the Chief Technical Officer of Voicera.ai, which produces Eva, the enterprise voice AI assistant. And I'm going to be talking today about the technical challenges in building a voice assistant for the enterprise in the workplace in general. So if we were to look at the most adopted collaboration tools in the enterprise, and we look at that sort of on a two-axis sort of system, that being whether they're structured or not, their format, and how much time an employee at an enterprise or a knowledge worker, if you will, actually spends time on it. So on the sort of structure side and sort of low time spent, you'll find enterprise apps like SAP and Salesforce. And as the format gets more unstructured, you find like instant messaging, SMS. I find email, of course, mostly dominated by Gmail and Exchange. Slack is also as sort of a messaging collaboration tool. It's pretty prominent these days. But if you actually look closely, you find that actually a lot of time is actually spent in meetings today. Voice in meetings is one of the mostly, lots of time spent in meetings, and it is highly unstructured. It's not a secret that many of us actually don't like meetings. Walk out of meetings, not really understanding, whether there's anything tangible, anything that is actually, actionable. It's highly inefficient. What did we agree on? What are the action items and so on? Funny enough, if you actually do Google search, this is what you get as auto-completion from Google for the search query that you perform. I haven't met anybody who actually likes meetings. There are few. Here are some very interesting statistics about meetings. So in the US, there are around 9 billion meetings yearly, and 100 billion globally. On average, people spend, knowledge workers and employees spend 37% of their time in meetings. And the average labor cost per 1 hour meeting is around $1,000. If you aggregate that over the Fortune top 50 companies, that's 75 million wasted labor. So they kind of remain the least sort of digitized modality in the workplace, and something is yet to be done about that. And that's what we embarked on in Voicera. We're trying to harness and activate the power of voice for collaboration. Voice is a very natural sense that we learn as kids, and that's what we use to interact in the workplace. But it's not done in the most efficient way. So we came up with Eva, the enterprise voice assistant, AI assistant, and Eva is your in-meeting AI assistant. We have a male version of Eva too, still settling on the name. The way it works, and I'll talk more about this, it's as easy as calling or inviting Eva at Voicera.com or Voicera.ai to your meetings. You interact with Eva through voice, hints that you give to Eva, or actually, if you like, you can manually tap on the screen to indicate what you want. Step 3 is you just review your email after the meeting and share, through Voicera. It's as simple as that. A really very low barrier to entry, and that's by design. I'll talk more about this decision and its implication on the technical side of things. So maybe now is a good time for me to give you a very quick demo of what actually Eva does. So that's the typical, that's sort of our web app. This meeting happened on Tuesday, October 10th. Right after the meeting, a few minutes after the meeting, you get this view where you can see the meeting. You can actually play what's going on.
Welcome to Blue Jeans.
This meeting was done over Blue Jeans. It was very simple.
Wait for a participant to join the meeting.
And so on, and then.
And 2018, they think it would be 10
there you go. That's the voice of Omar, our CEO. And just very quickly talking about the sort of the most important features here. You can see the agenda. This was input by the organizer of the meeting. After the meeting and after the meeting is indexed, which takes 10 to 15 minutes, you get this fairly interesting word cloud. The word cloud really highlights the most important and salient and interesting terms that were uttered and discussed in the meeting. So you can see the word daily. This is a daily meeting that we have, work fit our old name. And, click on revenue. It would basically take me to, well, the word revenue was uttered, 10th minute, I can listen to it.
The biggest source of revenue now?
And so on, I'll talk more about search and, how we did it.
They were going through the transition where the revenue was
a little bit. Basically you can search for anything here. Let's say I'm going to search for the word, experimental. We talked about some experimental features that we're actually, sort of playing with. And there you go. Here's the result. And as I said, it takes between 10 to 15 minutes to actually index the meeting.
Basically, think of it as like experimental or that.
There you go. And all kinds of UX features to sort of zoom in on something, certain part of the audio and stuff like that. So I've shown, the word cloud, and then the search capability. I'll talk a little bit about search later. Throughout the meeting, you can actually use a set of voice commands that Eva understands, using which you can actually highlight, we call these highlights, parts of the meeting that are interesting to you. And so, Omar here, our CEO, he highlighted two spots in the meeting at minute 23 for around like 14 seconds and another one for 20 seconds. These highlights initially are recognized by an ASR, then by an ensemble of ASRs, then they are proofed manually by users, and within 30 to 45 minutes, you get back a very high accuracy transcription of these highlights. These also get emailed to you, and afterwards you can actually share with people who were in the meeting or other collaborators, for example, here. We also have this nice sort of X-ray sort of timeline analysis of the salient parts of the meeting gathered by categories. So in terms of strong reactions, the word cool was uttered. There's a questions, the word when and who, and of course you can click on any of these and it would take you to the spot in the meeting that that this was uttered. Action item, the word follows, and so on. This is totally customizable. You can actually add any set of categories here that are relevant for you. So if in the sales organization, customer support organization, you can add the relevant. This is a very, very quick demo of our app that features Eva. I will talk more about technology here moving forward. I just thought I'd show you the most important features. But what I didn't show, but I'll be talking about, is the voice commands, the keyword spotting. But here's some very quick snapshot of the technologies that actually are used. Just keeping track of time. That are used in the in Eva. We have built our own keyword spotting, which we'll talk about in more details. Search and transcription are done through an ensemble of engines. There are actually 4 engines that are employed for this. And the main reason for using an ensemble, there are really 2 reasons: to improve accuracy significantly over the accuracy of any of the 4 engines used. And some of these engines were built in-house, but also knowing what the engines produced help us quite a bit in finding out where the errors are. And these errors are looked at by humans to be corrected. As this chart suggests, this is the price accuracy sort of compromise for transcription. If you use ASR, you get no more than 75% accuracy, 25% word error rate. Eva produces sort of near real time, less than an hour transcriptions with a near 100% accuracy at a fairly low cost. We still are in the process of determining the cost. The app is free for now for you guys to use. but we're talking about $10 to $20 subscription monthly. If you were to do human transcriptions, it takes 5 hours and above, and it's fairly costly. Practically you can do it in a one-off meeting, but cannot be a recurring service. We also employ lots of NLP techniques to actually compute our workload and X-ray as we showed. I'll be focusing more on the keyword spotting aspect of things and talking in technical details about what we exactly did. So the definition of the keyword spotting is essentially we have a certain phoneme sequence that we're interested in. In our case, it's the word OK Eva. This is the wait command. And we want to detect the phoneme sequence in the spoken utterances with a confidence. And we formulate this problem as a discriminative task, and I'll describe that in the next coming slides. So essentially, we want the utterance in which the keyword is spoken to have a much higher confidence than any other spoken utterance, in which the word is actually not spoken, the keyword is not spoken. And the most common measure of evaluating this is you can cast it as a retrieval problem in a precision recall manner. This means that AUC, which is the area under the curve, is really an interesting metric. Having said that, for this product to be usable, we're really interested in parts of the precision recall graph near 100% precision. And as I'm going to talk about the challenges, it's not really interesting to talk about an operating point which is lower than that, and that of course has a consequence in terms of recall. So what are the technical challenges that face us in building this? We wanted to start with a really very low barrier to entry. No device, no Alexa, no OK Google. And the most common communication device that people use there, and it's pretty easy to use, is the phone. So telephony was the least common denominator. Eva just dials in. Now that has a consequence, is that essentially using our telephone lines, some of them are capable of producing better than 8K, but 8K is it. It's the 8 sampling rate, and that really limits the quality of the signal that we're actually listening to. And we experience it as humans. When you talk to another person on the line, you can very well miss what they're trying to say or misconstrue what they're trying to say. There is another problem. Basically, when somebody dials in, they can be using the phone, they can be using any microphone you can think about. They can also be using various conferencing providers, which have a varying degree of the quality of the signal actually produced, depending on what kind of SIP stack and technology stack that they're using. And the meeting environment varies quite a bit. Is there an echo? Is there something in the background? And so on. So from the machine learning standpoint, for folks who understand what IID means, identically independently distributed, this is potentially non-IID problem. You could have trained your models on certain data, and you could be evaluating it or running inference on a very, very different distribution. And that actually happens, unfortunately, given how the wide variety of microphones out there. And I'll talk a little bit about how we actually handle that. There's also another problem. There's a very high cost of false triggers. If Eva gives a sound when it triggers the wait command, if that is a false trigger, it's very distracting to users. It can actually prevent users from inviting their friends. It kind of feels embarrassing, to it's like, what's going on? Why is she triggering when I didn't see the So precision is very, very important. We need this to run either on the cloud very fast, or on the phone or on the device. So it has to be very fast. It has to be a very small footprint. It has to handle different accents and different ways to actually pronouncing the command. The traditional approaches to keyword spotting is one of two: either limited vocabulary speech recognition, and the vocabulary being the sort of set of keywords, or good old traditional HMM hidden markov model, one for keywords and one for fillers. There's work as early as 1991 on that. Density models, generative models are interesting. They can work reasonably well for the distributions that they actually have seen, but they don't perform very well when they actually see something that they have not seen before. They also don't, because they're density models, they don't really focus, they don't end up producing very high accuracy because they don't focus on actually finding a decision boundary or on optimizing the margin per se. So the kind of accuracy that you get from them is not very high. We took a very different approach. We tried to cast this, as I pointed out, as a discriminant classifier problem. So what do? We try to basically classify context of frames as being the keyword or not, as this diagram indicates. So we establish a window size depending on the keyword that we desire to detect. The range is between half a second and 1.5 seconds, depending on the keyword. And this is a moving window that slides every 10 seconds. And it has to be big enough to distinguish whether the target word is uttered or not. It cannot be small enough to only detect part of the word. That can be confusing. That can cause false triggers when you utter part of the command. So in our case, OK Eva, if it's small enough, it would only capture the OK part, which can cause false triggers. So it has to be big enough. It doesn't. Of course, there's a big problem is that people utter these words by using a fairly wide dynamic range of sort of times. So it's kind of fairly tricky to determine the window size. Afterwards, we actually segment the window into a set of overlapping frames, something standard in speech recognition. Our frame size is 25 milliseconds, and we shift the frame by 10 milliseconds. Now, every frame is represented by a set of features, either MFCC or PLP or bottleneck features. These are fairly common representations that are used in the speech community. I'll talk about that later. It's very important. Representations play a big role in another aspect of our keyword spotter. And then the sequence of the frame representations are just input into a DNN. Let's talk about the classifier architecture. Now, the signal that I described is really a two-dimensional signal. There's the time dimension, which is where that's the sequence of frames as you transition through time. You move from one frame to the other, and then there's a frequency, because for every frame, typically there are like 13 features that are computed for every frame. Of course, it can be 15, but that's sort of the standard way of computing MFCC and PLP. So there is a time and frequency dimensions to the signal. It's a 2D signal. Now, guess what? I mean, this lends itself to a convolutional architecture that capitalizes on the proximity of features to each other. Proximity in time, that's very relevant because we transition across names, and proximity in frequency, because relative frequency coefficients that are close to each other means something. And convolutional nets are very good at capturing that. They showed that in the computer vision community. They're very, very good at capturing these sort of differences. Features are just not haphazardly sort of spatially distributed. So we have an input representation V, which is T times F. T is the number of time frames. F is the number of frequency components. And then we have this weight matrix W, which is essentially kernel M times R. And you have it's replicated n times, and we convolve it with V, the input. This spans across local and time frequency, and we do the convolution. The kernel size is M times R. Of course, we do weight sharing. Weight sharing helps to model local correlations. After the so-called feature maps, those that I just described, there is a max pooling area, a layer. The max pooling layer helps remove the speaking styles variability, because it actually pools. It kind of does averaging locally. So these variations kind of disappear or get toned down when you do the averaging. And there are 3 consecutive layers of convolution, followed by pooling. Then there are, there's a fully connected layer. Afterwards, there's an output. This is pretty standard. It's called sort of convolution architecture, amazingly enough, and fairly similar to the ones that are used in computer vision. So that's the main classifier architecture. There is something interesting about this problem. This is a highly asymmetric problem. If we were to look, if typically there, users invoke the voice command 3 times, maybe in a meeting, that's sort of, the average that we've seen. And if we're running every 10 milliseconds, just an easy back of the envelope calculation, you'll find out that, the positive to negative ratio is around 1 to 120,000, really highly asymmetric. Machine learning people know that learning can be very, very hard when you have such a distribution. And people deal with it in all kinds of ways. People train in a uniform way, or they up the sampling rate for the positive examples, create a near balanced distribution, maybe not quite balanced. And these techniques kind of work, but they're not bulletproof. Still, accuracy can be significantly harmed. Positive examples are really valuable, and they're hard to come by. So learning is hard. So cascaded classifiers are a technique that is fairly and has been commonly used in the computer vision and object detection world. One of the early very successful face detectors are the so-called Viola-Jones that really are based on a set of cascaded classifiers. So the idea is that you have a training set that has positive and negative examples. This in the diagram, this is what I call pool of keyword and non-keyword examples. And you just build an initial classifier with the prior distribution with this sort of highly asymmetric distribution. That's classifier 1. And you basically establish a threshold on its output, that if it is the output of the keyword, that if it is high enough, you will let it pass. If it's lower than this threshold, then you assume it's a negative example. And of course, the choice, we carefully choose this threshold to make sure that we don't lose any positive examples. We may get some negative examples to pass through, but guess what? These are hard examples that are were confused by the first classifier as keywords. So after we do that, we actually use classifier 1 to resample our training set. And only the negative examples that pass, that are not filtered out by classifier 1, and hopefully all the positive examples, because we picked the threshold as such, go into the training set for classifier 2, and so on. So every time, can easily see that the distribution that started being 1 to 120,000 gets better and better, because the vast ratio or percentage of the negative examples gets filtered out by classifier 1. So let's say then the distribution of training data on classifier 2 is more like 1 to 10 or 1 to 100 and so on, and the priors get better and better. Having said that, the hardness of the negative examples increases as we progress through the classifiers. So the classifiers, you find out that you need to increase the complexity of the classifiers as you proceed. Now, the good thing is that the vast majority of the windows that you run on only run on classifier 1, and so it doesn't really affect the mean inference time that you have 5 or 6 classifiers. It does affect the 99 percentile, because the interesting ones, the hard ones, actually have to pass through all the the set of classifiers. As I mentioned, this was widely used in object detection at some point in time, and even folks who actually use representation learning in DNNs, they end up building a cascaded set of DNNs for object detection. And one key, value or characteristic of this is that, as I mentioned, the distribution gets better. Although the examples get harder, but distribution gets better, and learning happens in a more favorable sort of environment. I'll be quick. We have 5 minutes. Another thing that helps us really reduce false positive is what I call, multi-representation approach. So one nice thing about the discriminant classifiers is that they're very good at determining the decision boundary, and they optimize the margin, most of them. The problem is if you feed something, out of domain, something that they haven't seen before, they can happily make an error and give you a very, very confident result, because they focus on the boundary, and who knows what the boundary between the classes looks like in the area that hasn't been seen in the training set. That's called the novelty detection problem. They're not very good at novelty detection, and it's a notorious problem for discriminant classifiers. So one way to overcome that's a fairly common technique used by machine learning practitioners, is that if I have a different representation of the input, equally good, the decision boundary that is going to be used by this discriminant classifier is going to be the same for the part of the distribution that I trained on. But of course, it's going to be a hallucination outside of that. But these hallucinations tend to be different from one representation to the other. And so if we ended up, building a set of classifiers, each using a different representation of the input, and we do model averaging in an ensemble of sorts, then on the areas that, this is a genuine, or something that I've seen before, within the distribution that I've seen before, they sort of excite each other, they don't inhibit each other. But outside of that, where there's novelty, they kind of dampen each other, inhibit each other. And this reduces false positives dramatically, because false positives are caused by hallucinations. The classifier hallucinates something, so oh, this is the keyword, well, it's totally not. And this is likely to happen, but it's unlikely to happen across different representations. We use 3 representations. We use the MFCC, null frequency, capture coefficients, and we use the PLP, predictive representations. We also use bottleneck features, which are actually computed using DNS. This is outside of the scope of this presentation. Something also very interesting that helped quite a bit in terms of accuracy, and this is the last thing I'm going to talk about before actually presenting some results, is that, I talked about classifying the window, and the window is just a mere part of the keyword. So, keyword is going to be likely represented by more than one window. To recall, we actually move the window every, sort of 10 milliseconds. So there's this cool thing in machine learning called multiple instance learning, and it was borrowed from the sort of medical diagnosis sort of industry. Is that when I do a biopsy, for example, I'm really interested, and I know this is sort of this sort of biopsy is benign, and I know that this is malignant. When it's benign, I don't know exactly which sample caused it to be malignant. All I know is that at least one of them is. While I know for sure in the negative bag of examples that none of them is. And there's a way you actually do learning without knowing exactly which positive example in the bag of positive examples is positive. So that's very similar to the window keyword concept, is that a keyword is represented by a number of windows, and I know for sure from my ground truth is that one of them, or at least one of them, is actually should trigger. And I know for sure for the non-keyword that all of them should not trigger. And there's a way to do learning without having to know exactly which window is positive. And so essentially the DNN I described is shared and is run on a number of windows. Afterwards, there's a noisy OR layer that aggregates the outputs of these individual windows. And multiple instance learning was proposed by Dietrich and Lathrop in 1989, and it was used in a number of problems, whereas this setup that I have a bag of examples that I know contain the positive example, and I know have a bag of words that I know for sure does not have a positive example. So we do the training accordingly, and we also use this noisy OR to decide whether there's a keyword or not. Because when a false positive happens, it's very unlikely to result in a sequence of positive examples. There's just a single sort of isolated a trigger window that actually triggers, and this helps us combat false positives quite a bit. These are the main techniques that we use to overcome the difficulties that I talked about earlier. Here are our results. And with that, we train a number of models for various keywords. On average, our model achieves a fairly high precision. This precision error, of course, very low, which will result effectively 0.0005%, which leads to a false trigger every 3-hour meetings. Below that, it can be very annoying during a meeting to hear Eva trigger while the user did not see the keyword. So it's very important. This comes, of course, at some expense in recall. So we get a recall of 90%, meaning that we actually miss 1 every 10 commands. The conversation being done over the phone, this is quite acceptable. We think from the cognitive standpoint, this is very common when you have a phone conversation with someone for you to miss some of the words they say. Of course, these results vary dramatically based on the microphones that you use. Some microphones are higher quality, don't incur any problems. Some are lower quality that are more problematic than others. We also have our training is actually running online, meaning that the meetings go on. These meetings cause triggers, which some of them are false, some of them are correct. We do label them, and we continue to train. And this causes us to be, this is one of the main reasons that we reach such a very high precision and able to operate at a fairly high recall as well. Finding false negatives, samples that were missed, is a bit trickier. Finding them is a bit more involved beyond the scope of this presentation. So that's it. I hope I gave you a good synopsis of what we do in keyword spotting and what Eva is all about. Please visit voicera.ai. You can sign up for free right now and use Eva. And I hope it's a useful tool for you. And please give us feedback if you have any. So thank you very much.